Welcome to the new era of video creation with Biozi. This is our new series on teaching deep learning. Today, we will discuss the activation functions. Here are the contents. Activation functions play a crucial role in neural networks by introducing non-linearity into the model. This non-linearity allows the network to approximate a wide variety of functions and solve complex problems. Without activation functions, no matter how many layers a network has, it would behave as a linear model. A linear model can only learn linear relationships between inputs and outputs, which limits its ability to handle more complex tasks like image recognition or natural language processing. The key to enabling neural networks to handle these complexities lies in the activation functions. The most commonly used activation functions are Sigmoid, ReLU, Tanh, and Softmax, each with different properties and use cases. In this lecture, we will explore how each of these functions works and discuss their strengths, weaknesses, and specific use cases. In a neural network, the basic operations performed by each layer are essentially linear. If we only used linear activation functions or no activation function at all, even a multi-layered network would just compute a linear transformation of the input data. This means that no matter how deep the network gets, it can only model linear relationships between the inputs and outputs, which is insufficient for most real-world tasks. By introducing non-linear activation functions between layers, the network can learn to capture much more complex patterns in the data. These non-linear functions significantly increase the expressiveness of the model, allowing it to solve problems like image recognition, where relationships between pixels, or features, are inherently non-linear. The ability of neural networks to approximate nonlinear functions is what allows them to outperform traditional linear models on tasks with complex data structures. The sigmoid activation function is one of the most commonly used activation functions, particularly in the context of binary classification problems. It has an S-shaped curve and squashes input values into the range between 0 and 1, which makes it particularly useful for modeling probabilities. The formula for sigmoid is fx 11 plus exfx, pan chien frac byn e1 plus ex is, where xx is the input to the function. The function is differentiable, which makes it useful for backpropagation, but it also has some key limitations. Specifically, at both extreme positive and negative values of xx, the gradient of the sigmoid function becomes very small. This is known as the vanishing gradient problem. This issue can significantly slow down or even halt learning in deep networks. Despite this, sigmoid is still widely used, especially in the output layer of binary classification tasks, where its output can be interpreted as a probability. The Tanh, hyperbolic tangent function, is another popular activation function, and it is mathematically similar to the sigmoid function. The key difference is that Tanh has an output range of 1 to 1, making it centered around 0. This centering can help improve training by ensuring that the activations of the neurons are more balanced, which can lead to faster convergence compared to sigmoid. The formula for Tanh is fx cha x e xx c xfx shak chash frac ex e shax e x plus ex, and it also exhibits an S-shaped curve, similar to sigmoid. While Tanh is more effective than sigmoid due to its zero-centered outputs, it still suffers from the vanishing gradient problem at large positive and negative inputs. This can still slow down learning in deep networks. Despite this, Tanh is often preferred over sigmoid for hidden layers in neural networks. The ReLU, rectified linear unit, activation function has become the most widely used activation function in deep learning due to its simplicity and effectiveness. ReLU is defined by the formula fx max soy ix fx psi ha max the x, meaning that if the input is positive, the output is the input itself, and if the input is negative, the output is 0. This makes ReLU computationally efficient because it involves a simple threshold operation. One of the major advantages of ReLU over sigmoid and Tanh is that it helps solve the vanishing gradient problem. Unlike sigmoid and Tanh, where gradients become very small for extreme values, ReLU maintains a constant gradient of 1 for positive inputs. This allows networks with ReLU activations to learn much more effectively, especially in deep networks. However, ReLU is not without its challenges, such as the dying ReLU problem, which we will discuss shortly. The leaky ReLU is a variant of the standard ReLU function designed to address the dying ReLU problem. In standard ReLU, neurons can become inactive when the input is negative, leading to a permanent zero output. Leaky ReLU fixes this issue by allowing a small negative slope for negative inputs, typically represented by the formula fx, max, x, fx, is, narmax, zalpha x, where an alpha is a small constant. This ensures that negative values still pass through, albeit at a reduced rate. Another extension of ReLU is the parametric ReLU, ReLU, where an alpha is learned during training rather than being fixed. This allows the network to adapt the slope of the negative part of the function based on the data, offering more flexibility. These variants help mitigate the dying ReLU problem while retaining the advantages of ReLU. The Softmax function is most commonly used in the output layer of neural networks that are tasked with multi-class classification. The Softmax function takes a vector of raw scores, also called logits, and converts them into probabilities, with each probability corresponding to a class. The formula for Softmax is fxi, xej xj fxa xi, chag t frac e on dxi, yes j e xj quine, where cxi is the raw score for class 2, and the denominator sums the exponentials of all the raw scores. This ensures that the outputs are in the range 0, 1, 0, 1, and sum to 1, making them interpretable as probabilities. Softmax is particularly useful when you need the network to choose one class out of several possible classes, such as in image classification tasks where an image could belong to multiple categories. Let's summarize the differences between Sigmoid, Tanh, and ReLU. Sigmoid is commonly used for binary classification tasks where the output is between 0 and 1, making it ideal for probabilistic predictions. However, its vulnerability to the vanishing gradient problem can slow training in deep networks. Tanh is similar to Sigmoid, but has a range of 1, 1, which makes it better suited for hidden layers in networks, as it's centered around 0. This centering can speed up convergence compared to Sigmoid. On the other hand, ReLU is widely used in hidden layers of deep networks because it avoids the vanishing gradient problem and is computationally efficient. ReLU is preferred for training deep networks, while Sigmoid and Tanh are used primarily in output layers for specific tasks like binary classification and regression. The dominance of ReLU in deep learning is due to its simplicity and its effectiveness in solving some of the key problems faced by earlier activation functions. ReLU is computationally efficient because it only involves a simple comparison between 0 and the input. More importantly, ReLU helps solve the vanishing gradient problem, which can hinder learning in deep networks when using Sigmoid or Tanh. Its effectiveness in practice has been demonstrated in numerous studies and has made it the default choice for hidden layers in deep learning models. ReLU's simplicity and performance in tasks like image recognition and natural language processing are key reasons why it has become the go-to activation function. While ReLU is widely used, it is not without its challenges, especially the dying ReLU problem. This occurs when a neuron always outputs 0 for negative inputs, effectively becoming inactive and not contributing to the learning process. In deep networks, if many neurons suffer from the dying ReLU problem, this can significantly reduce the capacity of the model to learn. Several solutions have been proposed to address this issue. The leaky ReLU allows a small slope for negative inputs, ensuring that neurons never become entirely inactive. ReLU extends this idea by allowing the slope to be learned during training. ELU, exponential linear unit, is another alternative that maintains a non-zero output for negative inputs, helping to mitigate the problem while still maintaining the advantages of ReLU. The exponential linear unit, ELU, is another activation function that has been proposed as a solution to the dying ReLU problem. ELU behaves like ReLU for positive values, but for negative values, it applies an exponential function, defined as fx ax1 fx, 1 alpha, EAX, 1, 4x, 0x, ReLU, 0. This allows ReLU to produce non-zero outputs for negative inputs, avoiding the complete inactivity problem seen in ReLU. The output range of ReLU is between A and I, where A is a constant. While ReLU performs better than ReLU in terms of ensuring all neurons remain active, it is computationally more expensive due to the exponential function. Despite this, ReLU has been shown to improve learning in deep networks, especially in tasks where neurons need to maintain some degree of activity even for negative inputs. Selecting the appropriate activation function depends largely on the specific task and the architecture of the neural network. For binary classification tasks, the sigmoid function is typically used as it outputs values between 0 and 1, which can be interpreted as probabilities. For multi-class classification, the Softmax function is preferred because it converts raw scores into a probability distribution across multiple classes. For hidden layers, ReLU is generally the go-to activation function because it is computationally efficient and helps avoid the vanishing gradient problem. However, for deeper networks or networks with very negative inputs, leaky ReLU and ReLU are better alternatives that can prevent issues like the dying ReLU problem. Ultimately, the choice of activation function depends on both the nature of the problem and the design of the network. One of the newer activation functions to emerge is Swish, developed by Google researchers. Swish is defined as fx, xs, x at fx, yash x, bar c dot, ash sigma x, where sx, a sigma x, is the sigmoid function. The function combines the best properties of both ReLU and sigmoid. It is non-linear and smooth like sigmoid, while also avoiding the saturation that makes ReLU so effective. Swish has been shown to outperform ReLU in several deep learning tasks, especially in image recognition. It allows the network to converge faster, particularly in very deep networks. The function is differentiable and smooth, making it a good alternative in scenarios where a simple ReLU might not be sufficient. To summarize, each activation function serves a specific purpose depending on the task and network layer. The sigmoid function is ideal for binary classification tasks, where the output needs to be interpreted as a probability between 0 and 1. The Tanh function is often used for hidden layers because it has an output range of 1, 1, which helps avoid some of the issues with sigmoid. The ReLU function has become the default choice for hidden layers in deep networks because of its computational efficiency and its ability to prevent the vanishing gradient problem. For multi-class classification, Softmax is the go-to activation function, as it normalizes raw scores into a probability distribution over multiple classes. Additionally, more recent activation functions like Swish have emerged, offering even better performance in some deep learning tasks.